Hi, so welcome to week 4 of the course on combinatorics at Stockholm University. So this week we have 2 videos. So here's the first one, so about Rook polynomials. You will find the material presented here in 8.4 and 8.5 of the book. And so what is this about? It's essentially about a nice little kind of combinatorial problem you can think about, but it's, as we will see, very useful also for more general questions. And so what we see here is a chessboard, so 8 by 8 chessboard. And there's this problem that if you, so you have to know what a rook is. So a rook is allowed to move horizontally and vertically. And maybe if you have 2 rooks, they can take each other, well, if they're in the same row or in the same column. And so if you have, for instance, 3 rooks, you have to, for instance, if you talk about non-taking rooks, it means that all these 3 rooks cannot take each other. That means, for instance, one would have someone here, another rook here, maybe another one here, but not here, because then they could take each other. And so after a while you might think, maybe, let's count it, because, well, we do combinatorics, we want to count things. So let's count all the possibilities to place 3 rooks on the chessboard so that they cannot take each other. And of course, since if you're a mathematician, you will always do everything in as large a generality as possible. So we will denote by Rn of C, where C is the chessboard, the number of ways to place n non-taking rooks on this board. Okay, so R0 of C is essentially, just by convention, it's 1. There's only one way how you cannot place any rook on the board. So what is R1 of C? Well, R1 of C is the number of ways to place 1 rook so that it doesn't take any other one. Of course, it's just the number of fields we have here, so it's 8 squared. So this is all much too easy. Let's go to R2 of C. Okay, so 2. Place 2 rooks on the board so they do not take each other. How do we do that? What is the answer here? Okay, so if you think about it, and in this case, you get well, so the best way to think about it, I mean, there are many ways how I can do it. That's why I'm kind of getting a little slow here. The one which is the best to generalize is the following. You think about it that you choose 2 different rows, namely this row and this row. You don't choose just 1 row, because that would mean that the 2 rooks would be in 1 row. And then you choose 2 different columns, like in this example here. And so how many ways can you do this? Well, this is a rule of product. How many ways can we choose 2 rows in here among 8 rows? Well, this is 8 over 2. Now the rule of product, same thing for the columns. We have 8 over 2 possibilities here. Now is that the answer? Nearly. But if you think about it, what we did, we just were singling out these little fields here. And so how many ways can we put in 2 non-taking rooks in here? Well, we can place them like this, but you can also place them like this. So we have 2 possibilities. So this is 2 times 8 over 2 times 8 over 2. And so let's do R3 of C to see where this leads us. Now we have to choose 3 rows and 3 columns. So maybe, as an example, let's take this one here. And so this singles out all of these fields. So we have now 9 fields. And so how many ways are there to do this? Well, choose a subset of order 3 and a set of order 8. So this is 8 over 3. Now multiplied with the same thing for the columns, 8 over 3. And now this is not yet completely correct, because for each of such choice in there, of a 3 by 3 subboard, if you like, how many ways can we put now in 3 rooks so that they don't take each other? Well, for the first row, we only have 1 rook in there. So we have 3 possibilities. Now for each such possibility, for the second one, we cannot take the same column, so we have 2 possibilities, and now we have only 1 for the last one. So it's 3 times 2 times 1, so it's 3 factorial. And now we easily see that once you understand how this is done, that what the general formula is, in this case, is n factorial times 8 over n squared. So this is the number of non-taking rooks. Okay, so after we computed these numbers, there is one definition one can make. So the Rook polynomial Rc, x is defined as the sum from n equals 0 to infinity over, so using the variable n from 0 to infinity, Rn of c times x to the n. So why is this a polynomial, and what we're doing here? Well, we're taking this sequence, Rn of c, and we're taking all of these numbers and put them together, just collect them together in a more compact object. So this is a priori just a series, but of course, how many ways are there to put 1,000 rooks on this chessboard so they don't take each other? Well, that doesn't really matter anymore. Well, they are just 0, so it's clear that this is a finite sum, so that this is really a polynomial, because for large n's this will just be 0. And so why do we do this? Well, there are 2 ways how you can answer this question. And one is, and this is like an example of what's called a generating function. We're going to talk more about generating functions later. And another one is that this actually makes sometimes computing these Rook polynomials, so these Rook numbers, a little easier. Because for instance, there's the following algorithm. Assume that you want to compute the Rook polynomial of a different board. And of course, well, if you know the Rook polynomial, you know all the Rook numbers, you know all of these numbers. So we're really interested in these numbers, but if you know a polynomial, you know all of them. So, for instance, of this one. So this is also a board. Well, it's kind of unorthodox looking board, but still it's a board here, and we can think about how many rooks can you put in there such that so that they don't take each other. And well, here's the rule how you can break this into a smaller problem. So R of c, x, the Rook polynomial of this board, can be computed from a Rook polynomial of board C prime and a board C double prime in a very easy way. And you find this formula. It's not hard at all in the book, nicely explained. But at least I want to tell you what is C prime and C double prime. Well, what you do is you pick an element, maybe this one here, and then you delete all the fields which are in the same row or column. So what we get is this little board here. This is C prime. And what is C double prime? For C double prime, we just take out this field. So we get this field. And so what is this good for? Well, this means that if you have a board, you can essentially now write a computer program where it just picks a bigger field, and then you get these 2 smaller boards, and now recursively compute the Rook polynomial for this smaller board and for this smaller board, and then just put them together in this way, and you will get Rook polynomial for the bigger board. And so if you break it into smaller and smaller pieces, that's the way how you can at least theoretically compute the Rook polynomial. So now in practice, of course, for small examples, it's much better to really do this by hand. because it's much easier, much faster. But for larger boards, it might be a way to do this. So I promised some application, and so the application is what's called arrangements with forbidden precisions. So here's our problem I would like to solve. And forget about the board for a moment. So we have a set A to A. So set A with 4 elements, 1, 2, 3, and 4. And set B with 6 elements, U, V, W, X, Y, and Z. And we want to find the number of injective functions from A to B, satisfying a bunch of conditions. And careful here again. So the statement is that I satisfy none of these conditions. So we do not satisfy any of these conditions. And what are these conditions? So condition C1 is that 1 goes to U or to V. Condition 2 says that 2 has to go to W. Condition 3 says that 3 goes to W or X. And 4 says that the element 4 goes to the element X, Y, or C. And so it looks like a really complicated problem to count these functions. So how does the Rook polynomial approach help here? Well, we will use the following board. We look at this 4 by 6 board, and we kind of translate these conditions here. So condition 1 tells us that 1 can go to U or V. In fact, well, we want to count those which do not satisfy this, but forget about this for a moment. Let's just translate these conditions. So I claim let's just shade these boards fields here. Now to W, so let's shade this. 3 goes to W or X, so let's shade this. And 4 goes to here. So what we get is, we get a board, and this board is called, these are the forbidden arrangements, so this is our board C. So the board C denotes the board given by the shaded field, so it consists of 1, 2, 3, 4, 5, 6, 7, 8 of these little tiles. Okay, so why is it called arrangements with forbidden precision? So what are the arrangements here? Well, think about what is an injective function. An injective function means that 1 has to go to one of these elements, and moreover, remember, it shouldn't satisfy any of these conditions, so it shouldn't go to here or here, so maybe it's here. Now 2 should not go in here, because it shouldn't satisfy this condition, the function. And so, but also it should be injective, so it cannot go in here, because then the function wouldn't be injective. 1 would go to X and 2 would go to X, maybe it goes here, and so forth. So here. So this would be one such injective. So this would represent one injective function satisfying none of these conditions. So these are the ones you want to count. And so if you think about it, well, this looks like an array, like a configuration of rooks, right? 4 non-taking rooks. So what we really would have to count is the 4th condition of the Rook polynomial of the whiteboard, the one which consists of all the tiles which are not shaded. And this is correct. This is one way how you can do it. Now, I want to present an alternative way which uses inclusion-exclusion. Why? Because this shaded, the board with the shaded tiles is much smaller. So it's easier to find out what the Rook polynomial is, what the coefficients are, instead of counting them for on the whiteboard. But in order to do so, we have to be a little careful here. So let's find out what the Rook polynomial is for the board C, and I just give you the answer. So this is given as 1 plus 8x plus I hope you can read this. So this is the Rook polynomial for the board of forbidden positions. So we want to express now the number we want to have in terms of the notation we've just learned about in the last lecture. So I claim that the answer should, in this case, is C1, this number. And I don't think this should be anyway now unclear. So what is the big S? This is the set of all the injective functions. And C1 is just this condition, C2, C3, and so C4. So we're counting all the elements in our big set S, the set of injective functions that do not satisfy any of these conditions. And now we can use inclusion, exclusion. Let's write it in this form. Like this. So this is the notation we also learned about. Okay, so let's try to evaluate this. And what is S0? S0 is the set of injective functions. So the number of injective functions. So we had a formula for this, so we can do it again. So we have 6 possibilities for 1. For each one of those we have 5, for 2, and so forth. So we have 6 times 5 times 4 times 3. Minus, now comes the big bracket. And now we have to evaluate n of C1 plus n of C2 and so forth. So let's just look at n of C1. N of C1 denotes the number of injective functions where one goes to u or to v. Okay, so let's pick just one of them. Let's say one goes here. Now, well, what about the other ones? Well, for 2 we have now only 5 possibilities because it should be injective. For 3 we have 4, and then we have 3. So it's 1 times 5 times 4 times 3. And now we have one more possibility by putting it here. So in total we have actually 2 times 5 times 4 times 3. And now let's go to n of C2. Of n of C2, same argument. We have only one possibility, namely putting it here. And now for 1, 3, and 4, we have 5 possibilities, 4, and 3 possibilities. So it's just, again, 1 times 5 times 4 times 3. And then we get 2 times 5 times 4 times 3. And then we get 3 times 5 times 4 times 3. So this looks very complicated, but if you simplify all of this, then multiply out 5 times 4 times 3, you get 2 plus 1 plus 2 plus 3, which is 8. And so we get 8 times 5 times 4 times 3. Okay, and I hope maybe you noticed already something. To make this a bit more clearer, let's write the 1 here. Let's write an 8 here. Okay, so let's do one more step. S2 consists again of n of C1, C2 plus n of C1, C3 plus n of C1, C4 and so forth. So let's just look at n of C1, C2. So this is the number of injective functions satisfying C1 and C2, which means like 1 goes here or goes here, and 2 has to go there. So we can either put them here or we can put these here. So we have 2 possibilities. And for the other ones, we already kind of chosen 2 values here. So we have 4 values left to choose from for 3. And for 4, we only have 3 values left because it should be injective. So this is like we have 2 possibilities here times 4 times 3. Now if we go for all the possibilities here we would have like 1, 2, 3, 4. Get like 4 times 4 times 3, and so forth. Times 3. And let's just see, so this is the same as 4 times 3 times, so multiply it out. 2 plus 4, 6, 12, 13, 16, 21. So this is the same as 21 times 4 times 3. And that looks good. And so now I guess you can guess what you can get here. So this is now 20 times 3. And finally plus 4 times 1. And so we see that here these numbers are precisely the coefficients in the Rook polynomial. And I really encourage you to meditate a little bit about this, why this is really true. And so in this case, if you work it all out, you get 76. And I really want you to also to read about this again. So let's read all of 8.5 slowly. If you have seen this for the first time, it might be a little bit overwhelming.